Okay, question 26. We have a sort of quantitative question on energy and work. So we've got 2.3 kilogram box, starting from rest, pushed up a ramp by a 10 Newton force parallel to the ramp. Ramp's 2 meters long, tilted at 17 degrees. Speed of the box at the top of the ramp is 0.8. Consider the system of the box ramp Earth. What is the change in the thermal energy of the system? Okay, so let's start as we normally do with a picture. Let's draw the ramp here, so it's not that 17 degrees of an incline. And we know that the ramp is 2 meters long. And then we've got a box here. Given its mass, and then it's been pushed with a force parallel to the incline. And we know this is 10 newtons. We know it's a 2.3 kilogram box. We know the length of the ramp is 2 meters. We know that this is 17 degrees. And we know the speed of the block at the top is 0.8. So, the box ramp Earth system only has one external force acting upon it, which is the work done by the hand. Again, the person is pushing. It's been pushed up. I'm going to assume this is the person pushing this box up the ramp. So the normal force that's on the box will be included because the ramp is in the system. The weight force on the block will be included because it's the Earth's in the system. So the only thing that's external into the system is I'm going to include this external force by the person. So the work net external on the block ramp Earth system is the work done by the person, and that's equal to delta E of the block ramp Earth system. Then we have to think about what types of energy. I'm assuming here. What types of energy do we have in a system? Well, we definitely have delta K of the block. There's a delta U of the block and the Earth. I guess I should probably have BRE in each of these, but there's definitely a delta U grav. I'll just ignore that speed here. Everything's complicated. Then we're going to say there's a change in thermal energy. So it doesn't explicitly state that the ramp is rough, but in order to have a change in thermal energy, we must have sort of a rough, must have some sort of frictional force acting on the block. So we're trying to figure out this delta E thermal, so I'm going to rearrange this equation. So delta E thermal will be equal to the work done by the person minus delta K of the block minus delta U graph. And we know that the person, work done by the person will be 10 times 2 meters, so 4 times the distance. We have this change in the speed of the block, we have this mass, and delta U graph, we can figure out how high it goes up on the incline. So we do have all that we need in this question. So this is the force by the person times the delta x of the block, and since they're parallel, I don't need any angles, I don't need the cosine. Cosine is just going to be 0, which is 1, equal to 1, minus 1/2 m bf squared minus bi squared minus this mg delta y. So the only thing that we sort of maybe challenging here is finding out what is this delta y. So you can go back to the picture here. This will be the delta y, and we can see that the sine of 17 degrees will be equal to the opposite over the hypotenuse. So if I just do this, so sine of 17 degrees equals delta y over 2. So delta y will be equal to 2 meters times the sine of 17 degrees. And that will give us delta y. You can also consider the x component of the weight force, which would be pointing down the ramp, would be mg sine of 17, and then you can just multiply it then by the total distance. So you can do it from a delta y analysis, or you could decompose the force. I mean, I'll just for completion of this problem, I'll just do that maybe down in this section over here. So if you consider the weight force mg, there is a component of it perpendicular to the ramp that does no work. There is a component parallel to the ramp which does work, and this will be the 17 degrees. So this piece will be mg sine of 17, and then all you need to do is multiply that force times the distance along the ramp in order to get the component. You can think about the work done by the weight force, and you need another minus sign in for that. But you can consider again part of the force that's parallel to the displacement, or just thinking about the delta y again, just in terms of the diagram. Both will give you the same answer. Okay, so we should be able to finish the problem now. So the delta E thermal is equal to 10 newtons. This is N times the 2 meter distance minus 1/2 the mass of the block. We're told it starts with push from rest, so I don't need to worry about that VI squared. I just need to worry about the final speed. That's all to be squared minus again the mass of the block. 2.3 9.8 meters per second squared, and delta y is going to be 0.58 meters. So we've got this work done here by the hand, subtracting the delta K and the delta G, and the delta E thermal works out to be 6.1 joules. Okay, so sort of as a summary of the question, I'll just note these answers here. So there's a very small change in the kinetic energy of the block, of only 0.74. Most of it this is a much larger number, the change in the gravitational potential energy of the block Earth ramp system of 13.9 joules. Sorry, 13.2 joules. So if you want to sort of think about it at the beginning, like what this person is doing. So the person's doing 20 joules of work. So they're pushing a 10 Newton force for a distance of 2 meters. The force and the displacement are parallel to each other. So they're putting 20 joules into the block ramp Earth system. And they're seeing very little change. Very little of that work is going into changing the speed of the block, going from rest to 0.8 meters per second. But they are moving it upwards in the gravitational field, so they're raising the block above the Earth, and that requires work. So a large amount of that 20 joules goes into just raising the height of the block by 0.6 meters. But these two numbers add up to 13.9. So the person could be asking themselves, well, I'm putting in 20, I'm only seeing a change of 13.9 in the sort of mechanical energy in the delta K and the delta U's. So where's the other sort of 6 joules going? Well, that goes into changing. There must be a rough surface here, so it goes into changing the thermal energy of the block and the ramp itself. So the temperature of the block and the temperature of the ramp, maybe plus some of the molecules that are surrounding the ramp and the block, would have slightly larger temperatures, and basically that's linked to energy. The molecules are moving slightly with larger speeds, so larger kinetic energy, but that's probably too much detail. But that's where the other remaining 6.1 joules is going into. So the person's putting in 20 joules of work, 13ish into the change in potential energy of the block ramp system, 0.74 change in kinetic energy of the block, and 6 joules-ish into the thermal energy of the block Earth ramp system.